Today we're going to be talking about non-ohmic elements in a circuit. Specifically, we're going to talk about Zener diodes. But before we can talk about a Zener diode, we have to have an understanding of what just a diode is. This is the symbol for a diode in a circuit. And the main idea of a diode is just to allow current to flow in one direction and not the other. It's commonly used in AC to DC converters to get rid of half of the AC current. In this situation, the diode will always allow energy to go through here, and ideally it'll do so with no resistance, just like an ideal wire. But if you try to put current the other direction, it'll block it. In real life, this isn't necessarily what happens. There's always going to be some amount of resistance going in this direction, and there's always going to be a little bit of leakage going in this direction. And diodes also have a voltage called the breakdown voltage, where current will be allowed to flow the opposite direction. Most diodes, this destroys them, and the breakdown voltage tends to be pretty high. This is the symbol for a Zener diode, and a Zener diode is very similar to a normal diode, where ideally it allows current in this direction with no resistance, but it's made with that breakdown voltage in mind. And for a Zener diode, it's called the Zener voltage, where it'll allow current to move through it very similarly as it would in the right direction, but it's a higher voltage before it allows that to happen. But it's made so that it can keep doing that for extended periods of time, a lot of times, without destroying the diode. Ideally, this is the graph for a diode. Essentially, perfect resistance until it reaches a specific voltage, at which point it'll allow current. And if you go for the breakdown voltage, where it allows current again. This can be idealized in 3 different ways, depending on the diode itself and also depending on what they're using it for. But this is the first one, where it's essentially a curve, where as soon as it reaches a specific voltage, it'll just allow a lot of current to go through. It goes up as a curve. Over here, it'll allow a certain amount of leakage to go through until it reaches some voltage, and then allow all of it. And then in this idealization, it's very much like the first one that you saw, where it's just perfect resistance up to a specific voltage, and then it goes straight up. And essentially the Zener voltage functions somewhat similarly, where there's some voltage where it's a very, very, very good resistor up until that point, and then it allows current. And this side of the curve looks very similar to this side of the curve, whichever idealization you use. And there's a very special characteristic that goes along with this, and it allows a Zener diode to be used to regulate voltage. Because if you look at this, you can compare it to a graph where you do current, voltage, and after a certain point, no matter how much you increase your current, the voltage will stay roughly the same, meaning it can be used to regulate that voltage. So you can test that in a circuit like this, where you have some voltage, some resistor put in series with the Zener diode, because Zener diodes can only carry a certain through them before they start breaking down as well. And that threshold tends to be about 200 milliamps. But in this situation, since the source voltage is well over the Zener voltage, this means that there's going to be 3.3 volts lost over this diode, and then the rest, which is 8.7 volts, will be lost over that resistor. And then by using this resistor and this voltage, we can find that this is going to have 17 milliamps of current, well below our 200 milliamp current maximum. And the reason that this is useful is that you can take it and put that diode in parallel with another component, whether that be a light bulb, a speaker, anything else. And whatever Zener voltage is being dropped over the diode, because it's in parallel with this, it'll have the exact same voltage drop. And this is good if your component has to have a regulated voltage going through it, just any sort of consistency, and especially in situations where your voltage source is going to vary. Examples include batteries, because a battery's voltage will change over its lifetime. So this is one way to make sure that even if the battery's voltage is changing, the component is always getting the same amount of voltage through it, and then once the voltage through the diode falls below a certain number, the circuit just dies and you can change your battery. So what we're going to be doing in our experiment is we're going to be varying the voltage in increments with a specific amount of resistance and observing the voltage drop across the diode, measuring the change in current every time we change our source voltage. And through doing that, we're going to hope to have a better understanding of exactly what the Zener diode's able to do.
This is our ingenious Zener voltage rig. So here we have our ingenious macaroni voltage varying machine in which we can insert more batteries or less batteries to vary the voltage through our rig. Upon leaving, it goes through this wire into this 470 ohm resistor. Upon leaving the resistor, it goes into this 3.3 Zener voltage Zener diode, the opposite way it should be, and then it comes over to this part of the circuit where this segment we will be able to insert an ammeter to measure the current, and it comes back into our macaroni rig where it connects back to the battery. So, after we connect the battery, completing our circuit, as my lovely assistant John will do right now, we will measure the voltage drop across the Zener diode over here with our multimeter, as you can see. See how it reads 1.5, which is what we expect with a 1.5 volt battery. And so this will vary until we reach the 3.3 Zener voltage, at which it will not increase anymore. Then we can come over to this segment and disconnect this piece, switch our multimeter into ammeter mode, and measure the current through our system, like so. And as you can see, it's a very little voltage, or very little current, because we're not yet at the breakdown voltage of the Zener diode. And we will continue this process, adding more and more batteries, like so. But this is a long and lengthy process, and to save you time, we'll put the screenshots of this chart after we do each run.
Now that we've collected all of our data, we can start looking at some of the trends that we see. At the very beginning, you start out with all of the voltage being lost over the Zener diode itself with absolutely no current. When you double the input, you'll see that a bit less voltage is lost over the diode with a very small current, and as you continue to increase the voltage, you start having a smaller comparative drop over the diode itself with a very rapid increase in the actual current. If you graph this, then you see that it creates a very interesting curve here, and it harkens back to the three idealizations that we looked at when we first introduced the idea of a Zener diode, of which these were the three.